Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, thanks for coming. We have an interview talk this morning with Piotr Mardziel, who's here from Maryland, a student of Mike Hicks, sort of a friend of the lab, and our group. And Peter does work on security and probabilistic programming, and is kind of well aligned with the interests of the group. And he's here to talk about modeling, measuring, and limiting adversary knowledge. Piotr.
Hello? Okay. You hear me? Yeah. Okay. All right, that's me, as you've heard. So this is mostly my thesis work. So it's you might notice it's maybe the full scope of the work is a little convoluted to fit into one joint piece of work, as you'd expect from a series of papers glued into one semi-coherent thesis. So keep that in mind. Okay. Some of you might have seen a webpage like this when you sign up to Facebook. And you might have thought about what happens to the information you provide to Facebook or to other online services. And there's some of you and myself might feel a little uneasy about providing this information for two reasons. One of them is hidden in these little terms and conditions when you sign up, which essentially say that Facebook owns your data, as in they can do anything they want with the information you give to them. And it's why would you feel uneasy having your information in Facebook and having them try to exploit your information to as full extent as possible? This is exemplified by this nice quote I found. If you're not paying, you're the product, right? These online services have incentives to use your information to the fullest extent possible to monetize it. And there's many examples of this happening in the real world. The most recent, I don't know if this is the most recent now, but Uber, the car sharing or taxi sharing service, got in trouble because they were keeping information that users did not want them to keep or did not even know that they were keeping. I'm not sure of the details, but users got up in arms over this. And the second reason you might feel uneasy is even if information is used as intended by these services, there is still bad guys on the internet that your information gets exposed to if it's stored on servers somewhere. So, and there's a lot of examples of this too in the real world, and I think the most recent one, most recent high-profile one, is this Sony data breach, where a lot of information about, I think, not just data, not Sony employees, but just users of Sony services, and even whole movies got leaked through some data breach. So either way, there is data misuse in these cases. There is either intentional misuse by these services or unintentional, where some bad guy comes in and steals their data for potentially nefarious purposes. So what is an alternative? Right? Could you wall yourself off from the internet and hide under a rock somewhere? Well, that's not a viable alternative, right? Because there's, first of all, there's friends on the internet. There's useful social interactions you're getting by participating in these services. And these services by themselves offer useful things. Maybe some of the, I don't know if any of you guys actually use some of these websites. There's Amazon, there's Dig, you know. You can imagine you actually wanting to use some of these things. You're actually getting something out of this. And by hiding yourself from these services, you're sort of removing the economic incentives that make these things possible to begin with. So it's unrealistic to wall yourself off from the bad guys, because you're also walling yourself off from these good things you want. So perhaps a more plausible alternative is to separate yourself but provide some interface for others to query your information for useful purposes. So for example, you might want these services to ask you questions. For example, this is a paraphrasing of a real query done by a Facebook advertiser that wants to offer you a cake for your birthday, or a coupon for a cake for your birthday. So they ask you, is your birthday within the next week? Okay, and at the same time, if you provide such an interface, you might want to look at questions of that reveal more information about you, like what is your entire demographic information. You want to say that that's too much information. I think this combination, I forgot zip code here, but the combination of birthday, gender, and zip code, which is the postcode United States, is enough to uniquely identify you. So that might be too much information. And other questions that you might want to be able to usefully answer are ones that collaboratively are computed among multiple individuals that try to protect themselves. For example, which one of us is oldest? So this might be it's hard to justify sort of these kinds of queries, but I'm just trying to present ones that are sort of approachable. But there actually are real-world queries in which you want to combine private and secret protected information to derive useful conclusions. And maybe I'll mention a little bit of those later. So you want to be able to allow these kinds of queries, but you want to have some way of detecting a query when it's too dangerous, and you don't want to. You want to make sure you sort of reject a query of that sort.
Are you thinking that this would just be based on the query, or it might be based on who's asking?
So it will probably be based also on who's asking. And I'll say a little bit more about that in terms of not naming individuals, but rather who has asked you what before. So you have to keep track of what people have asked you before. And that's it.
This picture implies some kind of central server, me, my PC, which answers all these questions.
Yeah, you can imagine that as essentially something under your control, your PC.
That's more or less what you intend. Perhaps a more efficient implementation, but that's the basic idea.
Yes.
Okay.
That's the basic idea, though. I'm not sure whether I'm not trying to push this idea as a end-all solution to misuse of information of the internet. It's just one interesting approach that you might see how plausible it is to implement this and see how far you can get into it.
So some things would become impractical, like sending cakes to people would mean you'd have to poll everybody on Facebook every week to see whether their birthday was this week.
Okay. So there's some design problems that you'd have to overcome to get something like this working. But if these advertisers remember, for example, your birthday, they would not query you this over and over again. And there's things that could be done to make this more plausible. So this problem is so the question is now, how do you distinguish these queries that you might want to answer from the ones that you want to reject? And so this problem of safe sharing is a very pervasive topic. Anytime any two people want to transfer one bit of information, one of them asks the question, should I actually transfer that bit of information? And the motivating scenario that actually funded my PhD studies comes from these coalition settings where armies in some theater of war want to communicate and share information from their sensor networks or their resources allocation, and they want to share it in such a way that does not allow someone who's querying this to sort of attack those resources. So for example, if the United States has a sensor network and they want to allow some interface to readings from that network, they want to make sure that those readings or a combination of readings do not compromise the network itself or the sensors that are producing those readings. So one thing that sort of colors my approach to this question of safe sharing is the distinction between online and offline. And it's worthwhile to briefly talk a little bit about what the distinction is between offline sharing and online sharing. So offline sharing is when you sanitize, you have some data you want to sanitize and release ahead of time to people who might want to use it for useful purposes. Whereas online sharing is you release information as it's requested from you. And so this has some strengths and some benefits, but some cons as well. First of all, when you're doing online sharing, you're tailoring the information that's released to the person who's requesting it. Whereas if you're releasing it ahead of time, you sort of have to figure out how to sanitize the data for everyone at once. And another con, a big con for online sharing is that you have to actually do this online. So you cannot just do this step ahead of time and be done with it. You have to wait for these requests and respond them as they come. But on the other hand, you do not need to know what information is actually of interest in the data you're releasing, because you can just wait for people to tell you what they're interested in. Okay, so given these distinction between offline and online and the sort of the requirements I presented for this sharing problem, there's some three initial observations that I want to mention. First of all, what does it mean for a query to be benign from a benign? How do you distinguish a benign query from a non-benign query? So that comes to the idea of risk. How risky is it to answer a query, for example, of this sort? There should be a zip code in there as well. So what happens if you answer a question of this sort? Maybe imagine that an adversary that gets this information goes out to a bank and fills out a loan application and gets a loan in your name and then your credit rating. I don't know if you have such a thing in the UK. You probably do. So, okay, so it screws up your credit rating. So there's a risk of something bad happening when you share information. And so there's a risk of a bad outcome. And in this talk, I'm going to approximate the sort of the idea of risk to just measure the probability of a bad outcome. And I'm not going to try to enumerate the bad outcomes. I'm just going to approximate it with this idea of vulnerability, which just says how likely is an adversary guessing your secret in one try. So it's just a rough estimate of what you might imagine risk is. So the higher the vulnerability, the higher the risk.
You're dividing your information into public things and secret things, and you don't want your adversary to guess the secret things.
Yes.
I mean, in practice, it's a bit more nuanced than that, isn't it?
Everything is more nuanced in reality, yes.
We don't really have information. I mean, it's the combination here that's secret rather than any particular piece
That
of
is true. But for this, I'm just going to assume that the stuff you're protecting, I'm going to measure the risk or the vulnerability of the stuff you're holding yourself and deciding to release. I'm just going to assume that the people you're interacting with, the queriers, have no other information about you to begin with as a rough start. So then the second observation is that risk depends on what you have already revealed. So for example, if you're deciding whether to answer the question, is your birthday within the next week, the risk in the adversary guessing your birthday after learning this very much depends on whether you've answered a question of this sort earlier. So you have to integrate, you have to take into account what you have answered before. And the final observation is that this cannot take a long time when you're doing these online sharing questions. Right? You cannot wait 5 months and spend 5 years worth of man hours to hire statisticians to answer this question for you. Right? This has to be automated. So altogether, summarizing all of these, here's the approach that my thesis attempted to take to solve this question of deciding whether to share or not in these online sharing scenarios. And the approach has 3 steps. First is modeling the adversary knowledge, which now is going to integrate the prior answers you've released. And then the second step is going to involve measuring a risk of a bad outcome. And I'm going to use this idea of vulnerability, which measures the likelihood of the adversary guessing your secret in one try. And the final step is going to be a way of rejecting questions that result in high risk. And all of that is going to be automated. I guess there's some disclaimers here that says that that there's some human modeling involved in this process. And so I'm going to separate the rest of the talk in these roughly 3 parts. These 3 pieces of work that I've done over my PhD studies. First, I'm going to start with a very simple example of all 3 of these modeling, measuring, and limiting steps in a simple example. And then I'm going to go to these collaborative queries that I mentioned earlier at the beginning. And if I have time, I'll say a little bit more about what happens when you're trying to measure risk as the secret you're protecting changes over time. Okay, so then the first work, this is joint work with Stephen McGill, my advisor Mike Hicks, and Mutaka from IBM, TJ Watson. Okay, so here's a very simple example. So this is meant to be extremely simple, so it's understandable to a vaguely general audience. So how do these 3 steps work for a very simple example? Let's say we have an adversary that has some prior knowledge. So this is step 1. You model adversary knowledge. I'm going to get into the details how I'm going to model this knowledge, but this is sort of a vague picture that describes the situation. First, we're going to model the adversary knowledge. Then we're going to consider, we're sort of going to speculate as to what is the knowledge of the adversary in the case where you decide to answer a question, and what is their knowledge if I decide not to answer the question. So I'm going to speculate about these two, and then I'm going to measure, is this amount of knowledge tolerable or not? And if it's tolerable, I'm going to answer the question, and I'm going to update my model of the adversary knowledge to the revised knowledge. And then after having done this, if there's another question that comes in, I have to speculate about what will happen after this second question is answered, and likewise measure risk. If that's tolerable, I'm going to answer, but if it's not tolerable, I'm not going to answer, and I'm going to recover the sort of the level of knowledge that was before I've answered that second question, and continue going on in this online manner. So that was the high-level picture. So now let's see a very simple example in terms of this. Cakes.com wants to offer you a coupon for a birthday cake, so they ask you this question, is your birthday within the next week? And you have to decide whether you want to answer this or not. So naturally, I'm in the programming languages group, so that question is a program. And this is a very simple program that just goes from your birthday, which I'm going to model as an integer between, as let's say 0 and 365, and it just returns true if your birthday is within a certain range of 270, which is today in some encoding. So this is a very simple program that just returns true for those 7 days around 270. So step 1 is modeling adversary knowledge. So the way I'm going to do this, I'm going to use a probability distribution that assigns a probability to each possible secret value. So it's going to assign for all possible birthdays between 1 and 365, the uniform value that the adversary, not knowing anything else about you to begin with, assigns a uniform probability distribution to your birthday. So this is actually not true in reality. Your birthdays are not distributed uniformly, but I'm just going to assume that it is distributed uniformly in this simple example. So this is it is knowledge. It's knowledge that birthdays are distributed uniformly.
Okay, there's no knowledge that's harmful to me.
Right. So far, it's nothing about you has been revealed. Okay. So what happens after you answer true to this question? So you do some elementary probability, and you compute what is the conditional distribution of your birthday, given that the output of this program, I'm just going to shorten as true here, but it's really this event that I'm conditioning over. And that just updates distribution to be uniform in the range of values between 270 to 276, where this is today. So if your birthday is within 7 of today, which is 270, this is what the posterior distribution of the adversary would be after learning that question, learning the output of that query. So the second step is to measure the risk in this knowledge. So what is the risk before you answer that question? So this idea of vulnerability I mentioned is very nice, because in order to calculate a vulnerability, all you have to do is figure out what is the probability of the most probable point in the distribution. So it's uniform, so they're all 1 over 365 in the prior. So the probability of the adversary guessing your secret is 1 over 365 to begin with, before they learn anything about you. But after they learn the output of the query, it's 1 over 7. So it is increased from that to that.
That's the probability of him guessing your birthday exactly.
Yes, in one try.
There might be a risk to him guessing your birthday to within a week. And
Sure.
that probability has gone to 1.
So there's different measures of risk. I'm going to use vulnerability for this talk, which is a very specific definition, and this is what it will give you.
So your definition is he guesses the exact number.
Exact number in one try.
Yeah, right. But guessing a close number might also be a
Yeah,
risk.
so you could use different metrics of risk, but for this example, I'm going to use this one. And so when I use vulnerability, this is actually I should say min vulnerability. This is a technical term that refers to exactly this definition of risk. So sorry, that might have been confusing.
I mean, so Simon saying the risk of guessing it's within a week. I mean, what about that? I suppose that's what you've answered.
Well, you're just saying, I don't care about that for the present purposes. But
for the
your users might. But you're.
Yeah.
But we're just. So you're just making an assumption here that we'll proceed with. Okay.
Yes, a simplifying assumption. Yes, questions?
Can I not learn something from you deciding not to answer a question?
Yes, I'm going to get into that next.
Okay.
So what about sequence of questions?
So I'm going to get into what happens after you answer this one, but then you have to answer another one. So I'm also going to...
Does the order matter?
Sorry?
Does the order matter? The order in which you ask these questions?
It probably does not, but I haven't thought about it. Probably not. Anything else? So I'm going to get to those two questions next. Okay, so then the third step was limiting risk via... So I'm just going to assume I'm going to have a threshold of vulnerability, T, and there is a lot to say about how you pick this T, and I'm not going to say anything about it other than this idea of vulnerability, which is a technical term, is very nice because it's measuring a probability of a bad event. So for example, you can use this if you have some metric that says if a bad event happens, the one I'm measuring, if the loss incurred when that happens is, say, L dollars, I should have changed it to just pounds. If you expected to lose L pounds once the bad event happens, and when the vulnerability is V, all you have to do is multiply them to figure out what your expected loss is, given that this measures a probability of the bad event. So there's other metrics, as Simon pointed out. There's a whole slew of other metrics you could use to measure risk, but I'm just going to use this one, and I'm just going to note that this one is actually pretty nice because it's very easy to connect it to economic quantities, which some other metrics might not be able to do. That's one possibility how far you can use this, yes. But then you should charge a little more, so your expected income is a little less greater than zero, right? Okay. So in this example, after you answer Q1, you speculated that the risk is going to increase to 1.7, which is less than 1/2, so that's tolerable. So I'm just going to say, oh, I'm going to answer that with true, and then, okay, so I'm going to answer true, and I'm going to update my representation of the adversary knowledge. And now what happens when I get another question? So now this is Q2, and it's the same question except the today value was updated by 1. So the advertiser is asking you the same question the next day. Okay, so so notice that for this question, if your birthday was actually 270, you should have returned true for this second query. Okay, so what is the posterior knowledge of the adversary after learning Q1 and Q2? It's exactly uniform in just one value, right? They learn exactly what your birthday is. So the risk in this is 1, because they have probability of 1 of guessing your secret in one try. Okay, so this is not tolerable. So do you reject this question? So unfortunately, if you reject this question, you get into trouble because it will leak information. So for example, consider what would have happened in the alternate world where your birthday was not 270, but it was 271. You would have answered true for this second question. In fact, you would have answered true no matter whether your birthday was between 271 and 276. So what this means is that an output true implies your birthday is within a certain range, and a rejection implies your birthday is 270 exactly. So the problem, as someone noted before, in that when you decide not to answer, the adversary knowledge actually increases. So this correspondence between prior and if I don't answer that they're supposed to be the same has been broken because there was a flow of information that you didn't account for. So the problem stems from a very simple design flaw that the risk measurement that I described to you and the way you decide to reject things depends on the value of your secret. That is, when you're computing this, when you're speculating as to what is the risk of answering Q1, you're checking what is the risk of answering Q1 with the output of Q1 on your real birthday, right? You're only checking what is the risk if I answer this with true. And true is the value of this birthday evaluated on your actual secret. So this whole procedure depends on this input, which is your secret. So this might not be clear, but maybe it will become clear when we describe this, the simplest possible solution to this problem, and that is using this thing called worst case vulnerability. And here, instead of just speculating at what the risk would be if I answer with the output of the query on my true secret, I'm going to speculate what will happen on all possible outputs of the query that are consistent with the knowledge of the adversary at that point. So for example, I would not just speculate as to the risk of answering Q1 with true, I would also look at what would happen if I answer Q1 with false. And if the risk in both of those is tolerable, I'm going to answer. And if either of them is not tolerable, I'm going to reject.
So would an extreme case of this be, say, if the adversary says, is your name Simon and your birthday 18th of January and your zip code CB1, and you would have to answer yes or no? Well, usually, for most people it would be no, and they would reveal very little.
Right.
For me, it would be yes, and I'd have revealed a lot.
Assuming that was a possibility, then you would have to reject.
And so for the worst case, then you're saying everybody should reject.
Yes, even if the people who are not you would have to reject. In order to be free from the case of them actually asking them the specific question as well in the future.
Can you use this to lie and then reduce your risk?
So lying is an interesting question, and I'm not considering any lying that is not modeled by the queries themselves. So you can certainly have queries that have non-determinism in it. For example, you can have a query that says, is your birthday within next week? And then with probability epsilon, flip the answer. So if you consider that lying, that's perfectly modeled in this whole scheme here, because the adversary is going to model that kind of sort of probabilistic query when they're doing this probabilistic revision. But lying without the adversary knowing what the nature of the query is, then I'm not considering that case, because it's hard to model that situation. Did I answer your question?
This is what if you want to reduce your risk, and then you just deliberately lie.
Yeah, so I'm not considering that, but I should say that you could, in expectation, your risk only increases, but in some cases when you have non-determinism and unlikely output happens, your risk might decrease. So that's a technical thing you have to, it would take too much to get into here, but it does happen. And that actually complicates the idea of how do you solve the problem of collusion when you're doing this with multiple people and you're tracking their knowledge individually. What if they collude? And then things get a little complicated. We can talk more about that later. Okay, so I mentioned earlier that this whole modeling knowledge and doing this probabilistic revision, everything here is trivial in terms of just elementary probability, as long as you have this wonderful tool called probabilistic programming, which, given a distribution of the inputs and given the outputs, lets you figure out what is the conditional distribution of this input given some output. So doing this is undecidable in general, and even when it's decidable, it's a little intractable. So what is the solution? So I guess the common solution in programming research is approximation, specifically sound approximation. So notice the way I described these probability distributions already suggested a way of implementing some representation of these distributions. For example, you would not represent probability distributions as sort of long list of probability values for each possible input. You'd represent it in some more concise or maybe abstract way, which I already suggested when I described these distributions, right? You might represent it as some set of regions that are perhaps behaving nicely with some probabilities associated with them. And so this is an abstract representation of a distribution that would otherwise be complicated to represent. And when you have to do these conditional distributions, for example, if you want to represent a distribution of the knowledge of the adversary given the output of the query was false, then you'd represent it as two disjoint regions. So this is the region in which the query would have been true. So if it was false, you have to represent it as two disjoint regions with probability bounds. But this is a much nicer and much more compact representation of a distribution over a potentially large state space. So the
same question the probabilistic programming languages need to address. That is, they could compute over probability distributions and have observations.
So this is probabilistic programming. So
essentially the answer is yes, it's the same. Yeah, it's the same issue. So it's quite a big lot. There's quite a lot of research work on this particular question. Yeah, right.
Although For me, there's a different restriction in that I want to be sound because I want to claim I'm doing security research, so I want to be sound in some sense. So my approach to probabilistic programming, the summary of the representation of distributions is these disjoint regions with probability bounds. So the over-approximation of a probability of each point lets you figure out a sound over-approximation of this vulnerability metric, because all it is the probability of the most probable point. But you also need to store an under approximation of each probability, because if you remember your Bayes rule, there's a quotient in there. And to do conditional distributions, you need to apply a Bayes rule, and you need to divide by a probability. So in order to get an over approximation of a probability after a conditioning, you need to have an under approximation of the probability of some events. That's why you store both of these to get a sound over approximation of the vulnerability. So this is an approximation of distribution. So having just these bounds lets you represent many distributions. So this is a good thing and a bad thing. A good thing in that you don't have to know the exact prior distribution of the adversary. You can just sort of envelope it in some abstract way. But it's a bad thing because this loses a lot of precision. There's a lot of different distributions that sort of fit into those bounds. All right, so the good thing and some bad things about this. So there were some other pieces of work I did in this part. So I already talked about this simulatable enforcement. So this is the idea that deciding whether to answer or not should not reveal information. So the usual solution to this is use simulatability, and that just means that the adversary can decide whether you will accept their question or not without actually interacting with you. And if that's the case, you can tell that your decision to answer or not cannot leak information. So sorry?
I didn't understand that last sentence.
So this simulatability is this idea. So I noted earlier how deciding whether to accept a query or not leaked information. And simulatability means that if the adversary can figure out on their own without interacting with you that you will accept them or not, if that happens, then the policy decision cannot leak information. Does that make sense?
That means that they must know my algorithm for revealing secrets, which might itself be a secret.
Okay, so I'm assuming everything here is public, and the algorithm I'm using here essentially models the adversary knowledge. So if I'm working under the assumption that the adversary sort of has a similar reasoning power to myself, and
he knows what reasoning I'm going to do, right?
Yes,
okay.
But on the other hand, if they're a rational adversary, they would do exactly this reasoning, that they will update their knowledge about you using a Bayes rule and things like that. There will be a Bayesian agent if they're trying to attack you in an optimal manner.
And you earlier mentioned that the decision about whether to reveal might be conditioned on your secret, which you hope they don't know. So if you're not doing the worst case thing, if you're doing the condition on your secret thing, then they're really not going to be able to predict what you say, are they?
Yes, and that's why you need to decide whether to accept or not based on your secret.
Oh.
And therefore making it simulatable.
I see.
And therefore not revealing anything.
So that's your claim. You should not base your knowledge on your
Right.
secret. I hadn't realized that. I thought
sorry.
Okay.
So that was the important part of that slide, where you're deciding true or false. You consider both those cases. Your secret is one among them, but the adversary knows this already. So you're not revealing anything new that the adversary didn't know when you're answering that question. So we can talk a little about that later, but let me continue to the next piece of work, which is very interesting. So this is joint work with my advisor as well, and Mutarka again, and Jonathan Katz, who's a cryptographer at Maryland, although this doesn't really involve that much crypto. So I mentioned earlier at the beginning of the talk of wanting to support these things, collaborative queries, when you want to answer a question that depends on secret values for multiple people at once. So since there is crypto somewhere, I'm going to use Alice and Bob as the parties, and I'm going to do everything from the perspective of Alice, and Bob is going to be the other person I want to interact with to do the computation. So the question like this, which one of us is oldest? I'm just going to assume everyone's born in the same year, so all you need to do to answer that question is compare our individual B days, B day A and B day B. So this too is a program. And let's say my birthday was 270 and Bob's was, say, 300. So you could try to do a similar sort of modeling, measuring, and limiting adversary behavior. But the first problem is, what if Bob themselves are protecting themselves and they don't want to reveal their secrets? So the first question you might have is, how is this even possible? How can I answer a question of this sort if I don't know what birthday is? So neither can I answer this, nor can they, because they don't know what my value is. So fortunately, there's this idea called secure multi-party computation, which lets parties compute a function of private inputs without revealing anything about those private inputs, just the final output of that function. So essentially, the crypto protocol that implements secure computation emulates a trusted third party. So it emulates the situation where the two parties send their secret to a third party. That third party does the computation and sends the final output. And the crypto sort of emulates that third party, which is not really necessary. They all do this in their heads. And the disclaimer there is the security guarantees of SMC is that nothing beyond what is implied by the output is revealed. But the stuff that's implied by the output might be a lot. So here's the picture of secure multi-party computation. You send your information to the trusted third party. They do the computation and return the final output. And in reality, there is no trusted third party. It's just fancy math. So how do we do this modeling, measuring, and limiting adversary knowledge in this case here? Okay, so let's do the first step. Let's just assume that Bob's prior knowledge about my birthday is the same as before. It's just uniform in a certain range. Okay, that's fine. So we did step one.
So who's the adversary here?
So Bob is adversary, we're Alice.
Okay, so Bob and Alice are mutually adversaries. It's not that there's a third party watching
Sure.
this.
So yeah, but we're doing this from the perspective of Alice, so we're going to call Bob the adversary. Although Bob will probably be doing the same reasoning as we are in this, because this is sort of a symmetric sort of setting here.
If Bob was the adversary, he might be perfectly willing to reveal his birthday to Alice.
Maybe, but I'm going to assume that he.
Well, down to the previous stuff.
Yeah. But let's say he's not. He's protecting himself too. Okay. So how do we figure out what is Bob's knowledge after return true? So the problem is that if we try to do this conditional distribution as we did before, we cannot do it because we don't know what Bob's birthday is. And so the problem is that Bob's posterior knowledge very much depends on what his secret is, which we don't know. So you can see the extremes of what his knowledge could be based on two examples. For example, if Bob's birthday was the largest possible birthday, right? He's the oldest possible. And if the question, is he oldest, returned true, that reveals absolutely nothing because it reveals absolutely nothing to Bob because he already knew he was the oldest. On the other hand, if he was the youngest and that returned true, there's only one possible value for Alice's secret, and that's 1. And Alice cannot distinguish between those two cases because she does not know what Bob's birthday is. Okay, so one potential easy, trivial solution is to consider all these possibilities and what I would call the worst case vulnerability. So as before, we considered what happens to Bob's knowledge when I answer true or false. Now I have to consider what happens to Bob's knowledge when his secret is 1 and I return true or false. And then what happens if his secret is 2 and I return true and false, and so on for all his possibilities, for all the ones that are consistent with my own knowledge. So this, you might imagine this solution is extremely conservative. So I think you already mentioned that the previous worst case vulnerability was conservative to begin with. Now this is even more conservative because if there is one possibility that Bob could learn a lot about me, I'm not going to answer this question. Even though 364 out of 365 times Bob's birthday would not be that one that would reveal so much. So this is extremely conservative. So another solution is you trust the trusted third party to do all this modeling, measuring, and limiting risk on our behalf instead. And the nice thing about the trusted third party is it's trusted to know the secrets of the individuals. So what you do here is you send the secrets to the trusted third party, you send sort of your policy thresholds to the trusted third party, and they do these policy enforcement and decide whether to answer or not on your behalf. So there's another problem here that it's sort of hard to see in that the policy decision that determines whether Bob will learn too much now depends on Bob's secret. And if Alice learned whether Bob was able to learn the output of a function, that secret might leak through that channel of information. So if Alice learned whether this is reject or accept, she might be able to learn something about Bob's value. So the solution to this might be not symmetric in that this process might reject one party, but might accept one party and give them the output. And it must be that the parties cannot see the other party's output. So this is a very strange situation because here we have Alice who has a policy, but she's not allowed to know whether that policy accepted a query or not, because that would leak information.
Is this, if you don't have a trusted third party, if you're just doing it with fancy math, is the fancy math capable of doing this too?
So theoretically it is, but I think the implementation-wise, it's a little out of scope of present implementations.
Okay.
Yeah. But theoretically, the fancy math can do any computation that you can describe, I guess, using circuits, and maybe there's some other models that...
So is this that homeomorphic encryption?
Yeah, it's related to that.
What you can do.
It's related to this, yes.
Or there's a slowdown of 10 to the 40 or something.
Yes, very big slowdown.
Okay, right.
Extremely big slowdown. Progress, yes. Okay, so that was...
I suppose it would also work if you really had a trusted third party.
This would work. But I guess all of the stuff I've been doing is trying to avoid having a real trusted third party, right? We want to do everything on our own. So I try to avoid that.
Even at the cost of 10 to the 40.
Yes, even if it's going to cost me a lot. Okay, so in this work, I described these two approaches. Then I did the simulatable enforcement that I just described. And even though this first approach was very conservative, I actually showed some example queries in which that conservative approach would still let you answer some queries, even though it's so conservative. And one common feature of those queries is just add randomness to the mix.
Do you have any sort of empirical results about that?
So I have looked at some queries. I didn't try to implement this in Epsilon C. I just sort of simulated if a trusted third party did this, would they answer these questions? So I only simulated sort of the policy decisions. So I have done that. So I measured sort of the risk involved if you answer these sets of queries to see that even the conservative approach lets you answer some queries. So you can look at this paper there to see that. So in the last few minutes, I'm going to talk about this case. What happens when the thing you're trying to protect actually changes over time? So far we've had sort of this model where we're measuring the risk of guessing your birthday over time as you're starting from your prior knowledge to the knowledge after you revealed outputs to various questions. Okay, so secrets change occasionally, so maybe not birthdays, but let's say you're trying to protect a location. Maybe you're using some sort of location-based service and you don't want to reveal too much about your location as you're doing this. So the first thing to notice is that once the secret's changed, now this sort of corresponds to a moving target for the adversary. Now they're not necessarily going to be guessing the sort of the same thing over time. They're going to be trying to guess the thing that changes over time, right? This is a moving target that they're trying to guess. And at the same time, when you're answering questions, you're not answering questions about your location at some time in the past. You're answering questions about where you are now. So the adversary is learning sort of this moving secret, the queries over a moving secret, and they're trying to guess at the same time this moving secret. So if here is a very simple picture of what this would look like. So I think there was a question of, can you recover risk? And so this is one situation in which the risk could lower. So here we have a situation where you sort of you have some prior risk and you're answering questions over time. So the risk increases, and at some point the secret changes. So maybe you move to a different location and the secret sort of drops down, sort of the risk drops down because now the adversary is no longer that sure of where you are after you've moved. And maybe this repeats. So if you have a knowledge threshold here in which you said, this is acceptable, on this side it's acceptable and here it's not, this might let you sort of keep yourself under that, in that acceptable range. But there's problems in here because real secrets that change over time, they're correlated. They're not completely independent. For example, your location now is not completely independent of your location in the past, right? There's even physical constraints, laws of the universe that prevent those things from being independent. And a very good example of this is, let's say if I told you at time 0 that I have a train ticket for London for Saturday morning, then if you think about what you know about my location for the next 24 hours, you might not be sure where I am 12 hours from now, but you're probably pretty sure of when I'm going to be Saturday morning. That means even if I don't tell you anything else about my location from now on, sort of the risk of you guessing where I am is going to increase with time up to Saturday morning, at which point you know exactly where I am. So this idea that the risk could increase without further interaction with me is sort of a very big problem here. So because this idea that risk could increase over time without further interaction, you really have to have some way of predicting the risk over time. You cannot just respond to this sort of in an online manner. You have to predict what's going to happen in the future. So the model in this work, we integrated this stuff from before. We had model of the adversary knowledge in the prior, but we also had a model of what the adversary believes is the correlation between secrets. I'm hiding a lot of details into this work because there's not enough time to get into it, but you can certainly talk to me afterwards. So integrating both these things, and since we're doing prediction of your risk in the future, we have to also consider what would the adversary do in the meantime, right? If I want to predict the risk of my location at Saturday morning, I have to consider which questions will you ask me in the meantime, or whether you're actually going to try to guess my location in the meantime. Right? So these asterisks that there's actually sort of adversary has some choices here what they want to attack. Right? They might be able to attack my location at the most opportune time, and at the same time they're observing certain things about me as time goes on. So if you interrogate both those things into this model, this picture changes. Instead of sort of going up and down, it's actually monotonically increasing. The risk is monotonically increasing when you consider optimal adversary behavior.
I didn't understand that. Why is it?
So this comes mostly from the fact that in the model here, we're assuming the adversary can decide when they want to guess your secret based on what they learn about you.
So if they ask me whether I'm going to London on Saturday, then over time they know my location on Saturday pretty well, but they really don't know very much about my location next year.
So this graph does not.
It doesn't monotonically increase.
So this graph is actually showing what is the risk, what is the eventual risk up to this point, which might involve the adversary guessing your secret earlier. So the point here is that, let's say I'm trying to figure out what is the risk at time 8. That might involve the adversary learning something for the first 4 time steps, and based on that information deciding to guess at time 4. So this measures sort of what is the expected probability of that bad thing happening up to this point.
The white line is not based on the grey one at all?
No.
It's using the same example. It's the same data. I don't remember what it is, but the only thing that changes now, the adversary is adaptive in terms of when they decide to attack. So the difference is between deciding when to attack based on what you learn or not doing that. So it's like an adversary deciding to guess where you are on a Wednesday, for example. That would be sort of non-adaptive, versus an adversary deciding to guess where you are based on what they're learning about you over time. So this adaptivity results in this monotonically.
The adversary only asks you at 3 and 4 and 7 and 8.
So actually, in this example, they ask you at each time step. It only changes at every 4 time steps. But still, given that they can decide when to guess based on the observation, this increases monotonically.
That's real data.
Yes, but this is a synthetic example, a very toy example. Yeah.
It's kind of trivially true that if you say, what's the risk that at time 8 the adversary knew at any previous time what my location was, obviously that's going to increase monotonically.
But they would have to so the measurement is they have to know that at that point. So it's not like you might learn something about at time 10, something about your previous time, but I'm not measuring that. The adversary has to know something about time 3 and a guess at time 3 in order to sort of take that into account. It's not like I'm measuring sort of the overall information that's released over time. I'm measuring their ability to respond to the information as it comes in. Okay, so there's an interesting thing here where you're trading off sort of recovering risk of the secret, but at the same time you're revealing more about how the secret changes. And there's an interesting example in the paper that the more you change your secret, the quicker the adversary can guess your secret, which is really strange. Okay, so that was that. So in terms of what I'm working now, I guess the most trivial thing is to make these things faster. The technology that is involved in doing this modeling and this inference, making this go faster. I'm also involved in a little bit about trying to get SMC faster. This is the secure multi-party computation, which is much slower than normal computation. I've done some work trying to get that faster. And this is an important thing which I think will be really useful, is to characterize this thing that I only briefly mentioned at the very end, where you have situations which you change your secret more often, and this leads you to revealing your secret quicker, which is really a strange situation. So I'm trying to characterize that in order to be able to figure out how to avoid that. And another thing I'm trying to do is, in all this work, I assume sort of the defender, we are sort of passive. Our secret might change over time, but how it changes sort of does not depend on what the adversary learns. So it'd be nice to look at, what if I actually respond to what the adversary is learning in order to decide how to behave. And then this gets you into interesting stuff and game theory and equilibria and all that kind of good stuff. Okay, and that's all I have for you. Do you have any more questions?
So is there any continuous distributions at all, or is it all discrete?
So everything I've done here is discrete.
The first part of your talk, when you mentioned that you were using a probabilistic abstract interpreter to calculate the risk, and so presumably that's an over-approximate analysis, right? So for example, if I use an interval domain, then I guaranteed that whatever risk I calculate lies within that interval. But you also said that it was sound with respect to vulnerabilities. So surely, I mean, you have an idea of what the probability range is, but you will make mistakes, right? So what do you mean by soundness with respect to?
So soundness in terms of the way I decide what is the vulnerability metric, I never underestimate that. I always overestimate that. And if you're using this in terms of having a policy that has a knowledge threshold, that policy in that sense would be sound, in that if you're ever, it will never say it's okay to answer when it's not okay. That's what I mean by sound.
If the policy is based on thresholds.
Yes, on a probability threshold, yes. Yes?
So your base assumption is that you get to answer all the questions. But in real life, what seems to happen is we reveal our information to Facebook or somebody, and their privacy controls say something like, oh, and we will reveal this piece of information to those people under these circumstances. And that, so you're kind of delegating your thing. And that makes it much harder to do this kind of centralized risk prediction thing.
Yes,
and yet, it's also the key to unlocking the value of, because you actually want Facebook to reveal some of your information to other people so that you'll get, appropriate adverts if adverts are...
Well, ideally, you wouldn't even send it to Facebook at all, but let Facebook be sort of the mediator between you and their advertisers, and let Facebook only just convey the questions they want to ask you and never send all your information to Facebook to begin with. I don't know how realistic this is, but that's the sort of the argument I'm trying to make, is that you don't ever let your data sort of out of your control. You're always in there deciding these things for yourself.
So that's rather different to these various authentication models that say, I'll reveal this information and delegate control over something.
Yeah, so no delegation. Everything is on my own.
You've already given it to Facebook, so it's kind of difficult.
Yeah. And I think the biggest problems with all of this are not technical but social, right? Who's going to go through all the trouble of not of getting rid of Facebook and getting rid of all these useful social interactions that are very convenient with Facebook, whereas this is probably not so convenient.
So I'm quite surprised you've not considered or lying, in
Yeah.
more depth, because I mean the sort of standard thing when you consider aggregate data, like in differential privacy, is you add some noise to the truth, so that the results don't reveal anything about the individual.
So I definitely allow adding noise to questions as long as that's modeled as part of the query. So for example, if someone wants to ask you a question but you don't want to reveal it as is, they can certainly ask you a question that add noise to it. Like if you don't want to answer a birthday query, I'm going to answer a birthday query plus a small probability of flipping the answer. Right. If they provide you with that kind of question, you certainly can model that situation and decide to answer that. As long as you model sort of the noise inherent in the question.
So what are the implications? I'd have thought that would make the system more flexible if the query is noisy like that.
Yes, so I certainly allow that, yes. And that's actually one of the ways
have you studied it? I mean, in what way is it really better in your study than not allowing the user to lie?
So the problem is here. What do we mean by lying? So if someone asks you a question that does have randomness in it, I wouldn't consider that lying. It's just I would consider that noising. Yeah. And it's a useful tool to be able to answer more than you would otherwise have, and certainly take that into account. And in a second work I described where I had these conservative method and less conservative method. That's one of the ways in which we've shown that you can answer questions even using the very conservative method, is adding noise at the end of these queries and taking that into account.
So I can see almost immediately, just qualitatively, that adding noise is going to allow you to answer more questions, and hence you're going to get more utility overall. But I mean, do you have any kind of
it's not about more, but more of a resolution, and in terms of it, you might have situations in which non-deterministic query could be revealed. So you have to noise it in order to be able to reveal anything at all. So it's not like, so the amount of information you're releasing, whether you're deterministic or not, does not matter. It does not increase the amount of information you can release. It just allows you to sort of get to a threshold closer than you would otherwise be able to do. If that makes some sense. Anything else?
More questions? Oh well, we're on the hour. Let's thank Peter.
Thanks, Peter.